Okay, welcome everyone. It's my pleasure to introduce our guest speaker today, Dr. Jun Ueda from Georgia Tech. Dr. Jun Ueda is an associate professor and bootstrap faculty fellow at the School of Mechanical Engineering at Georgia Tech. His research lies in the intersection of robotics, control systems, and bioengineering. So he started his faculty career in Japan, and he had visiting scholar positions and lecture positions at MIT before he joined Georgia Tech. So the topic for today is human-robot physical interaction for neuromuscular adaptive robot co-workers. Let's welcome the speaker.
All right. Okay. Thank you, Ju. Thank you for coming to my talk. So I'm Jun Ueda from Georgia Tech, and we have been working on a human-robot interaction study in terms of robotics. And then I want to introduce some of our work, recent work, and some old work very briefly, not going to very detail, but we want to give you an overview of what we are doing in terms of this project. Okay, all right. So I want to give you a couple of background of robotics work, but I hope that you are aware of kind of boom, some wave about robotic research. And I want to mention very quickly, but I won't go into very detail about some political side. But anyway, so robotics research is now becoming very important, and the US has decided to fund some money, actually lots of money, about robotics research. And then, so not Trump, but Obama actually made an announcement at CMU, several years ago at saying that, all right, so we are investing in robotics research. And at that time, he said, and also that this program is named National Robotics Initiative, it's a research program involving NSF, NIH, Air Force, and lots of other governmental sections. And they're saying that, all right, so we want to focus on research about co-X. Co-X means that, all right, human is still here, and robotic systems will support this person in various aspects. And for example, one of my, this is actually included in my title, so co-worker is, probably means that robotic systems which help human workers in assembly line, vehicle line or maybe aircraft assembly. So that's basically manufacturing focus. And then other ones, co-defender, maybe this implies some military application, right? So instead of you go there, the military locations, a battlefield, doing something dangerous, you could send robotic systems which help you complete your mission. So anyway, so the idea is that we create robots which directly support human activities. All right, and then Georgia Tech is very serious and very interested, also very serious about this opportunity, and we have started. So several years ago, right after I joined Georgia Tech, so we started center. Now it's directly under Georgia Tech's research portfolio. It's Institute for Robotics and Intelligent Machines, and it's a program across schools. So I'm from mechanical, and other people are from electrical engineering or biomedical or computer science, even some industry collaboration section. So we have big group to work on robotics research. All right, so we have some structure to do robotics research. And then, so my particular interests are, so today I want to talk about basically two human-robot interaction research, first one is rehabilitation, it's more about medical application. And second one is more manufacturing focus. So robot-assisted assembly, right? So, so the motivation, so this is something that you should have seen somewhere else, right? So we have lots of medical problems, right? So, for example, stroke after stroke, people have some problems in moving their limbs, and which is basically the remaining damage in the brain, and how we can help them regain their functionalities. And rehabilitation is very, very important. And so as a roboticist, we consider how our robotic technologies help this process, right? So, and I really want to help this. So help them recover daily functionalities. Okay, all right. And also, this some similar idea, but for the industry focus. So we want to protect workers, right? Worker disorders like back pain or neck pain. Some other portions you might get damaged because of the long-term physically demanding tasks. Then how we can introduce robotic system to mitigate this problem. So then how we can analyze the situation and how we can wisely introduce robotic elements into those settings. And while I work with a car company, and also we'll be starting some collaboration with aircraft company, which is close to the area of Atlanta. So I want to introduce some of our work, which we have been working on, that also we will be starting sometime soon, right? Okay, well, so, and my lab, so I'm not introducing every single detail about our work, but we are working on lots of robotic systems. And my background is motion control. So it's a technical term in mechanical engineering or system dynamics. So it's mostly about control of artificial standalone systems. So maybe robotic manipulator or maybe some robotic eye, so some assembly systems. So I grew up this area, but my research interested also human. So this is an artificial robotic system. And the other side is human. And the other side of the research is named a motor control. So you see the motion control, this is my primary area. And the other side, the motor control, that looks similar, but that's actually a technical term in neuroscience. And motor does not mean AC motors or DC motors, or geared motors. Motor means muscle, right? So this is about human. So my interest is mostly spanning between this. So controlled artificial systems and control of doing something good about human systems. And this looks very crowded, but shorter, the simpler version is this. So I want to work with both areas, but there are two approaches. And one approach that essentially I speak today is that learning, we have lots of skills, lots of skill sets which acquired in this motion control area, and how we can use this technology to help rehabilitation or medical or some process in humans. And this approach is basically called rehabilitation robotics or assistive robotics. Some of you may have heard. All right, and the other direction, so I'm not speaking about the other direction, but other direction is called bio-inspired robotics, or you name some other ways. But you learn human systems, or maybe some animals or insects, and inspired by the structure, how they are controlled, and then use that knowledge to design new systems. So two directions. So again, today, so I'm going to be talking mostly about rehabilitation robots or assistive robots, right? So the first topic is about rehabilitation robot, but I want to analyze this problem from the system engineering point of view. So first question is that, all right, so you may have seen or heard assistive robots, or so robots designed for rehabilitation. So something like this. So this is a robot, so it's not my robot, but a design at a Rehabilitation Institute of Chicago, so very famous rehabilitation institute in the nation. And so they developed, and this helps the gait training of stroke patient. So the robot system assists their limb movement, so leg movement, to help them recover their walking functionalities, right? So this is great, and this device has been used for a long time. So not only the US, but in Europe and some areas they sold lots of devices. But the question is this device really effective? Right? That's an essential problem. So is this device effective? Effective means that can we introduce more advanced rehabilitation procedure by using not this robot? Which means that we do not want to replace human therapists. Right? Of course, the replacement is one of the needs for developing new robots, but replacing robot does not create something new, right? So we want to do more than human-assisted therapy. So that's a big problem, and they raised that question, and then not very recently, but in 2009, that group published a paper about their long-term research about efficacy of this rehabilitation robot. And that paper actually reported some shocking result, saying that the robot is not effective at all. That's a shocking result. So it's also saying that it's effective, but the human therapy is more effective in terms of variability of symptoms, right? Because the subject of patients, the size are different, maybe kids or adults, senior people, and the different portions of problems. So then you have to be very adaptive. But this robot does not have that functionality. You have to have person, which is therapist, still adjust the mechanism. So this robot to do the therapy. So in that sense, so they concluded that, the robot will do the work, but did not bring anything so additional, right? That's kind of the argument, but this group actually reported this conclusion, right? So I'm interested in therapy, which we can do more than human therapy. So otherwise, we are not interested in that. Then we decided to pick a specific rehabilitation procedure, which is PAS, a paired associative stimulation. So I know that. So my background is not rehabilitation. So sorry that if you're not very familiar with this topic. So this is also new to me. Right? But I learned this one through my collaboration with medical doctors. And roughly speaking, so this pair means that you stimulate. So let's say you have some problem after stroke. You're having difficulty moving your limb. Right, so this is a damaged limb. So the idea of this PAS is paired, means that you stimulate the damaged muscle using, mostly electrical stimulation. You put some electrode and put some electric signal to stimulate that. At the same time, you stimulate the brain, associated part, motor cortex, with corresponding to this damaged part. So you combine peripheral stimulation and central stimulation by using, so this is electrical stimulation, and brain part is magnetic stimulation. So you see the figures. But combine these two, and it's reported that this is effective for functional recovery in some type of patients.
Excuse me. Sure. What kind of stroke would they have?
Oh, what kind of stroke? So this is
lesion.
hemiparesis, so which is incomplete. Incomplete case, not hemiplegia. I think you know what I mean, right? So patients are able to move, that not complete, not very smoothly, right? And this is mostly about upper limb, but I can tell you the why. So the upper limb. So and this are known to be effective, but this requires very dedicated setting in the lab. So it's not very directly applicable to general therapy, right? So on the other hand, this is my collaborator. So who has been performing this type of therapy long time. So you see that, what he does. This is a stroke patient, and he taps the tendon. You see that, taps the tendon and rubs the surface of the muscle. And also at the same time, he asks the patient to try to move the limb. So patient tries to create a motion, but that's not very smooth. But then he taps the tendon and also giving some stimulation to the damaged part to facilitate the functional recovery process. So this process has been, the clinical record is great. But also they have a problem. So this person is having seminars to teach young therapists, but for some reason, half of them cannot reproduce this result. And some of them could do, so which means that they don't know how to do this, but they know this is effective. So that's a problem. I saw that, we may be able to help them figure out what the mechanism behind this process. So I show this, but I guess you saw some similarities between these two, right? So the first one was that here you go. So we have magnetic stimulation to the brain combined with electrical stimulation, right? And the second one is that he asked, gave verbal cue, please try to move the limb, and tap the tendon, tap the tendon. So the modalities are different, but essentially the same, that they combined central stimulation and peripheral stimulation. So I might have said that this technique combines, stimulates peripheral and central at the same time, but that's not the case.
I just have a question. I've read about transcranial magnetic stimulation,
sure.
and it shuts off parts of the brain.
Shuts off the parts of the brain.
It reduces activation of the
So it produces activation. Yeah.
No, it reduces parts, and then other parts will come on.
Well, okay, so which we are not targeting, but we are just, focusing on the activation part of the brain.
Okay,
right?
so
we target a specific motor cortex to create signal to activate that corresponding.
Okay, so you're not interested in what gets shut off versus.
Well, we have started investigating about that.
I see.
Right. Yeah, inhibitory some system, but we haven't done that deeply. Right. But okay, so you saw some, but so giving this stimulation side, so it's not actually simultaneous, because if you tap the tendon or give the electrical stimulation, there is a traveling time from the peripheral, that part to the brain. So this timing is not zero. So then this is a timing matching problem. So you have to match this stimulation, the right timing, knowing this traveling time. Right. So for the upper limb, the traveling time is about 30 to 40 milliseconds, which really depends on the size of the big guy. It takes a long time. So there's a time delay. So then we decided to create a new robotic system, which actually mixes these two. So our device is mechanical tendon tapping device. So we took this, but we took the TMS, magnetic stimulation, right? So which is right, and I hope you can see. Oops.
This device is doing is it is combining a voluntary response or the
I don't know why. Okay, let me try.
What this device is doing is it is combining a voluntary response or the response that a person is sending from their brain, and it's combining it with a stretch reflex. So whenever we stretch a muscle, part of that neural signal actually goes up into the brain. And so if we time these correctly, we can actually make them combine together and excite enough so that it'll be able to escape the brain from that dead part of their brain and actually escape back down into the muscle, and we see a contraction of the muscle. We need to start understanding what's going on in the brain during rehabilitation of these stroke subjects so that we can actually improve them at a lot faster of a pace.
All right, so this is TMS, so the big magnetic coil targeting the specific part of the brain, so motor cortex. And that we combined this peripheral stimulation from the device, it's a very simple device, and magnetic stimulation to see if we have overlapping effect. Okay, and this is a result. So we gave mechanical impact because we are traveling time, so we have to give mechanical impact before we give TMS, and we change the time for magnetic stimulation and see if we have facilitating effect. So we do see, but there is a window, so 40 to 60 millisecond window, and if you miss this window, nothing happens. So that my argument was that if you ask, all right, so you have to give 2 simulations within 40 to 60 milliseconds by hand. You could do, but that's almost impossible. So, yes.
How is your brain magnetic stimulation localized or specific? How is it specific to each?
Before we do, so we change the location very. There's a device to do that. And then you click your device that actually moves to target a specific part of the brain. And then we manually tune to make sure that TMS is stimulating target here. So that should be okay. Right. So 40 to 60 milliseconds is still tight. But almost impossible. Still possible, but it's almost impossible. So my argument is that this is beyond human manual skill, but the robot can do a better job in this aspect. All right. So we found an interesting result in terms of the peripheral stimulation. So the PAS, this side, was originally used electrical stimulation. Electrical stimulation is basically impulse. Okay, impulse. So cubic impulse, there's a time delay, and there will be impulse, sorry, this is system dynamics terminology, impulse response in the brain. So that is very short period of time. So that is actually the window size is 10 to 20 milliseconds, even smaller than mechanical stimulation. And mechanical stimulation, so we have wider windows, which is better because it's a higher chance to hit it. And why? So we are still investing in that. But why this happened was that the difference of modality. So we tap the tendon, and then so in the muscles there are receptors called muscle spindles, and there are a lot of muscle spindles. And even if you tap, so there are lots of them. So some of them fire early, some of them fire late, which means we have lots of impulse responses, right? So which creates a series of pulses which creates a larger window. So then using mechanical stimulation actually makes sense to improve the success rate of this therapy, right? So okay, I'm come back to clinical side soon, but let me talk about a little bit of the robotic side, all right? So and the robotic side, so we use the pneumatic device. The pneumatic device is air pressure, pressured air controlled simple cylinder, right? So which is the requirement, because we wanted to test this device eventually in MRI, so magnetic resonance imaging scanner. So you cannot bring ferromagnetic things, then either plastic or a brass. Brass is okay, but you cannot bring AC/DC motors. Then pneumatic systems are great fit. All right, but some of them may be thinking that pneumatic systems, air pressure, right? It's slow, right? It's slow. The speed of response is not enough, because I'm talking about 40 to 60 millisecond time window to match. All right. So some of you may be wondering, all right, so speed of response of pneumatic system may not be great enough. But so we should not mix two requirements, right? So what we want to have is the small variability, all right, which is the repeatability of this timing control, not the speed of response. All right. So pneumatic system has pressure attenuation, time delay. But as far as we have good model of the system, we can compensate it, because we don't need fast speed of response. As far as the system repeats the same procedure over and over again with very small change in time, then that's okay. So the pneumatic system actually very good at that. All right. And then so we quickly tested the variance in time delay or impact timing. And those are within 2 to 5 milliseconds. So 2 to 5 milliseconds and given 40 to 60 milliseconds. So that's okay. Fast enough. All right. And then we tested. So this test, we tested this under, so this is one of the, just ended NSF Engineering Research Center program. So at headquarters was the University of Minnesota, but we are one of them. And then I collaborated with Vanderbilt University, and they studied this pneumatic system control. So the pneumatic system, this is a cylinder, and we have reservoir. There's a long transmission line to bring the device into MRI. And usually we have long hose about 7 meters or 7.5 meters, so long. So the time delay and pressure attenuation, of course. And so what we observe in terms of the difficulty of control of this pneumatic system is the pressure. Basically, we control pressure. And we want to control the pressure of the cylinder chamber inside of the MRI, right? And our controller is outside the MRI, so through this long transmission line. So we want to measure the pressure inside here, but we cannot bring in the pressure sensor, because pressure sensor is not MRI compatible, because packaged with some stainless case, right? So what we could do is only to measure pressure right after the reservoir. So it's the valve, okay, valve. So some people make a measurement, okay, which I mean here, all right. Some people make a measurement of line pressure, if we are allowed to bring in, but which is not exactly the chamber pressure. But lots of people actually believe that, that blue line pressure is the same as chamber pressure. Actually, they are very different. So the change of the pressure is very different. So we want to control the pressure in red, but what we can measure at this moment in this setup is only green. right? So that's time delay and pressure attenuation. So our idea is, well, very straightforward. We create a model of the whole system, so nonlinear system and compensating. Right, so I won't be talking about detail about this modeling, but we have a model that worked one graduate student, and then we, okay, I cut off this one, but so we created a controller with the device, and then we close the loop, and now we have, that's the observer, then some backstep control. So if you're interested, please let me know later, but it's too much detail about the math, sorry. Right, so we close the loop, and then we applied pressure control and accuracy, and then now so old technique is in, this purple, solid purple, and then new method, our method, in terms of error, is those, right? So we got order of magnitude, actually two order of magnitude better result by using this method. And then speed, even though we are not interested in speed of response, so 2 Hz speed of response is twice higher than any existing pneumatic control. So our device is much faster and much more precise by using this. So that backed up by this technology, we implemented our mechanical stimulation device, or this procedure, to do that brain stimulation. Okay, all right, and going back to the human side. So we are interested in, this overlapping with between peripheral stimulation and central stimulation happening. And we measured EEG, which is a brain wave type of measurement. And then, so we haven't completed this, but analyzing where this overlapping is happening. So whether it's in the motor or sensor, and then we are collecting data. So we are seeing something similar. This is a known result about stimulation of electrical stimulation, but we should see something that we saw something like this with mechanical stimulation. So we see some delay because the timing is different because the stimulating modality is different. So mechanical stimulation versus electrical stimulation. But once we see something like this, we can say that, all right, so we are confirming this overlapping effect in some part of the brain. Right. And then, so the last one, so this, we are still working on data collection, but biggest question is, can we, by using this robotic technique, can we help the facilitation process, right? And this is the result, well, the only one subject, but so we performed our therapy for this time, and this will increase kind of the facilitate, means that the increased activity in the brain, right? Which lasts about 50 minutes. And because of the brain plasticity assumption that if we continue this, keep doing this process over and over again, this increased activity remains forever permanent in the brain, so that you can create a signal which goes out from brain all the time and reach the limb, and you can move the limb, which is basically a cure. So this, well, so it's not conclusive that this is a promising result that this robotic therapy may be used for future rehabilitation, right? So, but our argument is again, so this.
Just one question. So, this is one patient?
Yes.
One experiment, or repeated over different days?
Well, so this is one patient. That's correct.
So one patient just trained for 50 minutes.
Just for training for 50 minutes. So we gave about, okay, I didn't do this, but so PAS, we provided this therapy for initial, 15 minutes, and I saw how the facilitation of this LTP changes over time.
Right, so my question is, this is all happening in one day, one experiment?
That's correct. Then this is not a great data.
So
I
you
agree.
don't know whether...
Right, so we cannot say anything conclusive. So so this is not it.
Gotcha.
Okay, all right. So, but our argument is that so this therapy is pretty much timing control. So timing control of two modalities, then which is the robot system is very good at that. All right. So now, so we are working on how we can adapt the subject barrier variability in the subject. So we tested about 15, but I'm showing the timing window of each individual subjects, and they are very, very different. So then we have to adapt, to tune the timing, and then that's almost impossible to measure all the time ranges and figure out the window. Then we are using some sort of machine learning technique. So this is it's a very simple Bayesian estimation, but we sample the data and then estimate the distribution from the sample data. And then based on the estimation, we take new sample and then create the complete estimate of the distribution. So this is one of the results, but originally we had this distribution in blue, and by using this Bayesian estimation, we got red only with, I guess, four samples. And the original one was 28 samples. So you can drastically reduce the time to estimate the possible time window. And then we can start the therapy, right? So this is a direct application of machine learning technique, but this is working okay, right? Okay, and then now these days, recently, we started collaboration with another group. This is a portable version. A portable version is a mechanical hammer, and mechanical hammer is the traditional device. But now we have accelerometer and then some tablet communicating, and we collect acceleration input and figure out, so your tapping is correct together with some therapy, right? So it is a kind of IoT application of this therapy, the simpler version, right? Okay, well, all right, so then switch the gear. So far I've talked about how the human system responds, adapts to robotic stimulation. And this is something along the same line, but this is more about assembly application, well, mostly. So this is a project with General Motors, and they do this every day. And then, so the robot assisted task. So, and we have something similar set up at Georgia Tech, and investigate this assembly process. And our target, our problem is here. So problem is that if you control, okay, you see the vibration, right? So if you control robotic device, and there is roughly fight between you and robotic system, because robotic system is a standalone system with sensors and actuators with some controllers in it, and we are also the complete system. We have sensors and actuators, and we move our limbs based on our intention. All right. So there's a time delay and also haptic stability problem. Even though two systems, all right, our system should be stable, and you can control the robotic system stable, but there is no guarantee that if you combine two stable systems, there's no guarantee that the combined system is stable, right? So actually, this happens as vibration, right? So then the GM actually was very concerned about this because they broke doors, engines because of this, and then we start collaboration. So, and we figured out, we tried to figure out what the problem here is. One is that muscle stiffness, how we use muscle, and how we use multiple muscles. And what is happening here is maybe terminology, maybe next one? Okay, maybe core contraction. Core contraction means that, so when we try to stop the hand robotic, lift, so we are programmed, we are programmed to grasp the handle harder, create activation of multiple muscles to stop it like this. So it's a contraction, co-activation. But because the muscle tissue is nonlinear, actually this increases the stiffness. So to make the stiffer seen from the robot. So then when we do this, robot senses, okay, so robot senses handle is now fixed, but it has to move it. Then it creates more force. Then we sense it, then we stiffen our arm more. Then robot sense it, then it creates vibration. So this is a really bad story. So this happens when we try to stop it. Other cases where our muscles are very relaxed. So our system is changing depending on the situation. So our idea is, okay, once we measure this mode change, right? So relaxed mode versus the stiff mode, then we can change the robot controller to reduce vibration and make the system stable, right? Based on measurement and later estimation. Okay, well, so the estimation modeling part is that this is very simple pick and place task. So move the part from one place to the other and put let's say a door to the vehicle body, right? So task is very simple. So we saw that we measured how we means that operators change the level of core contraction, right? So here's the result that when operator interact with relatively stable with no vibration, then level of core contraction is lower than the case where the system is oscillatory. So which means that when we sense devices creating oscillation, we tend to create greater oscillation and make it stop, right? Right. So which, again, it creates a huge problem, of course, then we have to do something. Right. So I can skip this, but our idea is that now our system, so human operator, changes the status of how he or she uses muscles dependent on the situation. And that's one of the parameters in the system, which is basically stiffness, so like spring element, and which changes, well, high to low or some middle, but the human system, there's distribution. Okay, there's distribution. So it's not switching between two determinist systems, actually switching of stochastic system or random system. So we have to treat our system as a stochastic system, not deterministic system. So there's a framework to do this, as a feedback control. But together with a classifier. So classifying technique is that the operator is now contracting muscles at higher level or lower level, right? So based on this result, we change the robot operator to make the system stable and also not to reduce the performance. All right. Okay, and here's another one.
When the robot detects that the person is trying to hold the device steady, it actually slows down the motion and adds damping into the system so that it moves more smoothly and is easier to hold in place when they need to. And then when the person relaxes again and the robot detects that they're trying to move the device over a distance again, it then removes that restriction and will move quickly again. Basically what we're doing is we are taking some sensor measurements of the person and trying to make the robot smarter. So typically robots are designed just in a vacuum. The robot is designed as the robot and that's the way it works. But what we're trying to do is give the robot some knowledge of the people that will be using it to make that robot more intelligent and more user-friendly.
All right. Well, so the first phase of this project, we use a sensor measurement, so EMG, so the muscle activity measurement, to change the robot behavior. So it turned out, of course, it makes sense, but if we change the robot behavior based on human activity measurement, sometimes that change is too late, right? So it's already vibrating and start crushing important parts, then that's too late. Then we actually saw some vibration, so for the measurement-based power system. So like it makes sense. We measure muscle activity, and the muscle activity height, and we modified the robot gain. So now robot takes over the task. Then the operator doesn't have to produce much force. Muscle activity decreases, robot decreases its force. Then the worker has to produce more force. It's oscillation. So even though we don't see oscillation at the end effector level, but still we are seeing oscillation in muscle level. So which is still a problem, which means that measurement-based robot control is not the right way to do. Then we have to predict it, right, before this happens. So that we are working on prediction of human intention. So we are using multiple models, but now we are using some layered hidden Markov model. It's kind of a switching model with multiple layers about human modes. And then we model this and then made prediction. So okay, I can go very quick. But so what we did was that, so by using data, several data in the past, so sampling time is very slow, with 50 milliseconds, and 3 to 7 points sample to make a measurement about what the next possible state would be. Right. So in that time horizon, 1 second, 2 milliseconds. So for most of the assembly tasks, we want to estimate what happens in next second. Okay, next second. And before the robot breaks important parts, we want to switch the robot mode. So this by using this, maybe 3 or 4, not as many, but as far as we have good database to predict human intention, we can make a measurement. Right, and then we compared, and well, so far, so layered hidden Markov model works okay, and so other SVM or other techniques also work, but we see some changes in the estimation scores. Right. Okay, well, and also interesting about human-robot interaction. So I mostly talked about still robot side, right? So how we estimate the human and how we can eventually change the robot behavior. But this human-robot interaction context, both are responsible for, which means that we can change the robot, but we should change the human behavior because human is also an important piece. Then this is a training protocol for human workers. So how, well, workers can use multiple muscles better way. All right, so the training protocol is very simple. They have physiology research, but so we measure EMGs and give instruction. All right, so use 2 muscles, contract, and reach at a certain level as quick as possible. And by repeating this, then we expect that this person should be able to operate a robot in a better way. Right, so we are try to improve both sides. Okay, not only the robot, but also the human side. Right, okay, and then this, actually, I can, because this is, repeat of what we have. But right now we have just quick. All right. So we have. Okay. Here. All right. So our Okay.
By taking physiological measurements
right now
from the
we
human
use a
operator,
gaze tracking
such
system
as
and pulse
electromyogram
sensor,
or EMG
Pneumatic,
data,
combine
as well as
everything,
eye
make
tracking
prediction.
data, we
And
intend
change
to compensate for the
behavior based
operator's
on the measurement
stiffness
that
and therefore
information.
improve the stability and performance of our system, leading to smoother operation.
Okay, so this is very long, so I can move ahead. All right, and okay, other topics are I can introduce very briefly. So other human-robot interaction, physical interaction related topic. So this is a DoD project, rescue robot project, collaboration with Georgia Tech and University in Korea. And we create remote control robot to rescue site, a nuclear disaster. So, and my job is to, okay, this is the Korean side, but so they have remote controlled excavator, so which is great, and how we can introduce nice controller to control those robots remotely. And my job is to, well, model human-robot interaction, so it's a human side and robot side, something similar, like, as I explained. And then we control, so idea here is that we introduce some autonomy to help us process, which means that, so we have some, our limbs and also our joystick or controller to control the remote robot, which has a different structure, right? So the direct mapping of your motion into the robot does not guarantee the nice operation. Then we have to modify the input based on some knowledge of the system. So we are proposing to introduce some autonomy. So the automatic system, well, automatically corrects the motion or the geometry of the input command for the robot to operate complete the operation without breaking something. Okay, well, so that's what we are working on. All right, and then so this is another project with Georgia Tech Research Institute. This is Jetpack. All right, Jetpack has been there for a long time, but for some reason, not some reason, but there's a clear reason that the DoD has not approved this device because of UCY. This is the human safety. Right, the flying is okay. Okay, landing is much harder, right? So this is about 100 kilograms, right? Very heavy, right? 300 pounds. All right, so again, flying is okay, landing is hard. So then my job is not to create flying robot, but actually landing here, so which is the exoskeleton. So, and this is first version, so we created a leg protective exoskeleton, and then we measured EMG and some force feedback, and we see that some reduction about muscle activity and joint loading. Right, this is ongoing work, but this is, so we found that, so this body protective exoskeleton is very, very different from human augmentation. So human augmentation, that's wearable robot, and so that helps you carry much heavier something, or gait assisted. So this is not assistive device at all. This is a protective device, and the functionality is very different. And we are working on kinematic analysis of this device, but so this device have to have two modes. The one is muscle and tendon protection. The other one is bone and, well, basically joint protection. So they are completely different functionalities. So I would say they are orthogonal to each other. So because you damage muscles and tendons when your limbs move much greater than the range of motion, right? So this moves. And on the other hand, you would break bones when your limb directly receives external load. So they are 90 degree different, right? So then our exoskeleton should have two functionalities. These two, oops. That's Microsoft, sorry. Oh, that's bad. Okay, all right, give me a second. Oh, it's really Microsoft. All right, well, anyway, so we are working on those, and then, oh, great. All right, and then we are working on, all right, great. Well, anyway, so, and we developed this. So, but idea here is that to protect muscles and bones at the same time, we have to have two connections to the limb. One is a parallel connection for muscle protection and serial connection to protect bones. So, which actually makes sense, but I've never seen other exoskeleton which have this structure, because most of them are focused on only one of them, right? So, but yeah, we are working on this, and then this is some detailed analysis of kinematics, but it's okay. All right, and then so along the same line, so we are also creating exoskeleton robot for construction worker safety. So this is, again, body protection, how we can help them, reduce the risk of back pain, for example. Right, and then there's a guideline under NIOSH, National Institute of Occupational Safety and Health, which is under CDC. And we actually talked with them, and then we haven't started the project, but so we decided to create a new robotic or exoskeleton, and I can skip this, but that's this. So this is still, that doesn't look fancy, but it's the first prototype. But this robot is not to augment the power of the worker. It is preventing risky posture. Only when the worker takes risky posture, that too much bend, for example, then some actuator will move and bring the body back. All right. So this is not an augmentation story, right? It's protection or just only to change the behavior of the workers. Right. And then so we spoke to them, and then we actually influenced the CDC's policy. So this is their blog, but so we talked to them and we told them, all right, we need to investigate how the worker's behavior changes when he or she wears exoskeleton, and then we have to do those research, and then actually they posted on their blog exactly what we told, all right? They may have stolen, okay, they have stolen our idea, but that's okay. So you are influencing some research portfolio is under CDC and NIOSH. Okay, all right. So, okay, so maybe I'm running out of time. So this is my last slide, and this is the graphical conclusion slide. So, so I explained, so only one idea. So using motion control knowledge to help human systems in terms of power-assisted rehabilitation therapy, power-assisted robots, body protection, or worker posture, behavior, some correction, right? So, we recently published two books, and for this one, so actually the Professor Danny over there, so he kindly contributed this work. So we're very happy to be able to publish this this paper, this book, which looks great, but also that other actuator works, we published the other one, and recently those books are published. So you don't have to buy, but just want to announce that we did those works. All right, and this is the last slide, and the work, most projects are supported by NSF and DoD and General Motors, and I would like to thank my collaborators and mostly our students who contributed to those projects. And thank you very much, and I want to take any questions that you may have. Thank you.
Before we move to the question section, may I know who has the sign-in sheet? Oh, okay. If you haven't signed yet, please do so after the talk. It's very important for the Institute. And having said that, any questions for our speaker?
Sure.
Yeah.
So, what I found especially interesting was this communication between the robot and the human. So, seems awfully similar to someone learning pottery or any other metal work. So, how can you codify the interaction between the robot and the human? Do you think that just specifying it as a natural language is sufficient, or do you think that you can give these instructions to either humans or robots in a specific language, like say you have a finite machine and some other way where you can make these things much more simpler?
Okay, you mean some verbal, some communication, how the both sides communicate each other. Well, so our DoD project. So maybe this. All right, could be this. All right. So our DoD project. So my area is mostly a human-robot physical interaction. So which means that we have some mechanical interface. So maybe a force sensor or handle. So which for the operator controls the handle, then we can sense the operator intention through force or displacement information, right? And then so we use the gaze. So the other project, we use the gaze information for the robotic system, the automatic system to figure out what this person is trying to do. And that's one. And my collaborator, so he's in civil engineering, Georgia Tech. So he uses voice information. Speaking language, but that it's getting better. But I'm not sure that the voice recognition is good enough to introduce this type of very critical situation. But some groups, including this group, have started voice recognition technique to communicate. Right, and then from the operator side, so we display haptic. What we say haptic information is a force feedback. Is one of the useful modalities, but it's not the only way to do it. And lots of people use this, with a screen and then bar graph, so a color, change of color or sound to inform some information to the operator.
You had two questions earlier.
Sure. Thank you for the talk, Professor. This is in regards to slide number 39, that you mentioned predicting intention for impedance control, I think.
Okay.
Yeah, so my question was, how exactly do you define intention here? What variable are you trying to
okay. So intention is, at this moment, our intention is all about state transition. Okay. So this diagram. So we have a couple. So this is a very early one that we use, but we are just focusing on the assembly task and the pick and place. So then the student actually manually picked those states and then created a state transition matrix. So, and based on this, we created layered hidden Markov model. So, but we have Markov model created based on this, and there are a couple of sub layers behind. So then, in terms of intention, then it's basically one of them. One of them is the intention that we are using.
So you use it you pose it as a classification problem.
That's correct. Yeah. So we have discretized intention based on this
Sure. And what time horizon over which are you making these predictions?
Well, so that is about a few seconds. So for assembly task, so we need up to 1 second. Then that's probably enough. But of course you can extend the time horizon. But yes, we are focusing somewhere around.
Thank you.
I was curious about this stiffness predictor. If you envision any application for rehabilitation.
Rehabilitation. Well, so it's not our work, but my collaborator in physiology is using something similar to mechanical vibration to, actually trick the reciprocal inhibition. Okay, so he's there doing so mechanical vibrators to actually change the network of the reciprocal inhibition, where eventually that changes the stiffness of the therapy for, I forgot the name, but that's specific therapy for, not the stroke patient. Okay, I forgot the name. Yeah, but there's some application to this modality.
Just kind of curious, like if you have published any papers on the
jetpack.
Yeah, the jetpack.
Good question. We haven't published a paper yet, but we are planning to do so sometimes. So yeah, we are collecting data for motion capture data. See if we are decent, statistical significance about the change of muscle activity. So yeah, we are collecting data. Yeah, but we broke the that prototype, and then now we are fixing it. So then once we get that fixed, then we should be able to get more data and get the paper published.
Thanks.
Stay tuned.
Okay, let's thank the speaker again. Please sign up at the back of the room.